So this is the title of my talk, and I will present some results I worked on together with my colleagues from NICT in Tokyo, as well as from Louisiana State University. In this talk, I will discuss something about boson sampling, something about compressive sensing. I will discuss conditions under which boson sampling is classically simulable, and I'd like to apply some results related to these things as a tool for molecular vibronic spectroscopy, which I will also discuss later. And then in the second part of my talk, I will pose a general question if quantum computing can be useful for compressive sensing, for general problems in compressive sensing. So let me start with some basic introduction to boson sampling. So what is boson sampler? Boson sampler is nothing else than an interferometer. So here we have some unitary transformation. Here we have, as the input states, some specific states I will discuss later. And then at the end, we measure the output in each mode using some photodetections. So we are interested in the joint results of the joint measurements from these photodetectors. And sometimes I will also discuss the situations with photon number resolving detectors here. So it's not necessarily just a photodetector, but it can be also like photo counter. So this boson sampling setup has been particularly interesting after the famous paper by Aronson and Arkhipov, 2010, in which they introduced the so-called scattershot boson sampling, in which the initial state is is single photons input to several modes, and then in the rest of the modes there is vacuum. And then they showed that statistics of the joint measurements in this, or just statistics of the output from the joint measurement is equivalent to finding permanence of some matrices related to this unitary. And then a permanent is defined like that. You can think about it like something similar to determinant, but with all pluses everywhere instead of pluses and minuses like in the determinant. And this small detail, the lack of minuses, actually makes the problem of finding the determinant of like big matrices difficult for classical methods. But it is not always difficult. This famous paper actually discusses the case in which the matrix here is a complex matrix, and moreover, it is chosen from chosen randomly from a Haar distribution. So, and in this particular case, you can show that there is no classical known algorithms to find that permanence. Therefore, it is believed that this problem is classically difficult.
So can I ask a short question here?
Yeah.
So do these two authors actually prove that boson sampling is sharp P, or what do they actually prove in this case?
Yes, I think, yes, it is sharp P. Okay, so, but later, people also came up with some other setups which also are similar to this and are also classically hard. In particular, we have the result from 2014 in which people introduced this Gaussian boson sampling. In this case, the input is Gaussian, then the unitary is also Gaussian. So the output before the measurement is also Gaussian. So entire this evolution can be calculated classically efficiently. The problem is with sampling actually from the Gaussian state, because this will be non-Gaussian measurement. And then it is not so obvious how to calculate probability of finding particular number of photons in a big Gaussian state. And then also people show that this problem is equivalent to finding so-called loop Hafnians. And then here I defined this loop Hafnian. So the definition is very similar to this. We somehow must this sum is over the set of perfect matchings in a matrix equivalent to this. And then what is perfect matchings of a matrix of perfect matching of a graph? So we define perfect matchings for graphs. In this case, perfect matching is the set of all pairs of nodes in the graph, such that each node is paired to just one node. So in a graph without loops, we can distinguish that for instance 1 and 3 and 2 and 4 is a perfect matching. In a graph with loops, we can also distinguish that, let's say, 2 and 4 plus 1, 1 and 3, 3 is also perfect matching for the graph with loops. So the loop Hafnian then is defined like here we have the sum over all perfect matchings in the graph. So you can imagine that if the graph is larger, finding all perfect matchings actually is difficult. It is like it's a difficult combinatorial problem. And especially also with these additional loops, you have much more combinations. Okay, so for us, it's just we just need to observe that or remember that a loop Hafnian is also difficult to calculate classically. In a sense, it is we don't know any in general, in fully general case, we don't know the efficient algorithms to do that. Okay, so in this case also, somehow we discuss, so this paper found the necessary, actually the sufficient condition, the if condition for the problem to being classically difficult, but it is not a necessary condition. So actually we don't know necessary conditions for the problem to be classically hard. And therefore people discuss different classes of problems such that boson sampling, let's say, is actually solvable classically. So not any case of boson sampling is classically unsolvable. And in particular, okay, we will discuss a case in which boson sampling is classically simulable efficiently. And our results, our research was motivated by a proposal to apply boson sampling for some boson sampling as a quantum simulator of some physical problems. And then we observe that in physical problems, you usually don't have a complex Haar random matrix here in this unitary, because physical problems are somehow always, you have some symmetries, you have a lot of properties that can that make this matrix actually not Haar random. Therefore, this result classically hardness cannot be, sometimes may not be applied to some physical problems. So I will discuss this later. And now, because we are in Vienna, the city of music, I will make a short digression about music. And I will need this example later as to show some analogy. So this is a drum. To tune the drum, you use these screws. And then the vibrations of the drum can be described in terms of the so-called normal modes of vibrations. And then you can imagine that when you start, when your drum is vibrating in some like ground vibrational state, and then you tune, then if your tuning is adiabatically, then you may finish in the ground state after the tune. But then if your tune is like sudden, then it is more likely that when your drum is initially vibrating in this ground state, then after the tuning, it will vibrate in like several different modes. Okay, so I go back to boson sampling. Is boson sampling useful for anything? So after this paper, 2015, the authors of this paper proposed to apply boson sampling as a quantum simulator for Vibronic spectroscopy, where Vibronic means vibrational states vibrational change of a molecule associated with electronic transitions. So imagine a molecule which is maybe in its ground state, ground electronic state, and then actually the molecule, vibrating molecule, you can think about it like a drum, but the drum will be now will have much more degrees of freedom than the normal drum, because each molecule can somehow move separately. So now, instead of just two-dimensional vibrating system, we have a multi-dimensional or multi-mode vibrating system. But the analogy with tuning the drum and with electronically exciting a molecule is still valid, in the sense that somehow in the ground electronic state, a molecule has a given structure, and then you can define normal modes for this particular structure, and somehow when you excite the molecule to the next electronic level, the structure can change because the forces in the molecule change. Therefore, the normal modes also change. And then if your molecule initially vibrates in a basis mode, so let's say it is 0 temperature and the molecule vibrates only in the ground state, then after this excitation, it's like after the tuning, you can excite the molecule to many, so that the molecule can be found in many excited states in different modes. And actually, the number. So each like that normal mode can be described as like quantum harmonic oscillator. Therefore, we associate these creation annihilation operators with harmonic oscillators. There are bosonic operators. And then one can somehow observe how the bosonic operators are changed after the excitation, electronic excitation. So this can be found from observing how the structure of molecule is changing with when the electron is excited. So when the electron is excited, the forces in the molecule change, and somehow you need to define the new normal modes. And then if the normal modes are transformed like that, then you can observe that your vibrational creation and annihilation operators change in this way. I think this prime is an error here, where these constants are defined over there. Okay. Then we need to add that finding all the transitions from a ground vibrational mode to all possible vibrational modes of the excited state is a difficult problem, because there are so many possible excited states. Because if a molecule has, let's say, 10 atoms, then the number of degrees of freedom is like 3 times the number of atoms, so it's something like 30. And then in each of degrees of freedom, you can have this normal mode and many levels of your harmonic oscillator. So somehow adding the next just one extra atom to your molecule, you add some harmonic oscillators, and then you multiply the number of possibilities by the number of levels of the new thing. Therefore, the number of possibilities you need to consider is scaling exponentially, actually, with the number of modes or with the number of atoms. Okay, but then we observe that this bosonic transformation is actually a Bogoliubov transformation, which can be simulated in any bosonic system. So actually, you can imagine that it's not so difficult to imagine a photonic setup with the same transformation. And then if we have it, we can say that the output of this transformation, the result of this transformation is the same as the result of excitation of the molecule, and then the sampling of statistics of single photons is the same as probabilities of finding an excited molecule in some particular vibrational state. Okay, so this is the conclusion of this paper. But then, like I said, motivated by the observation that actually the real spectrum of molecule even is typically sparse. So there are just a few non-zero or significantly larger probabilities than for just a few transitions are more probable than entire set of all other. We propose such a theory that when the boson sampling is sparse, then a boson sampling is classically simulable. When the output of the boson sampling is sparse, then boson sampling is classically simulable. Okay, so how we prove it? We consider only partial measurements. So we say that somehow we observe only measurements from 2 detectors, ignoring the rest. So in this way, and then we want these marginal distributions from different pairs. And then this is an idea from compressed sensing, which said that if the joint distribution is sparse, then the marginal distributions uniquely determine the joint distribution. So in our case, we concluded that if these marginal distributions we observe here somehow are efficient to find, plus some algorithms from compressive sensing are efficient, then we can calculate everything classically. So is finding marginal distributions for partial measurements like this for, let's say, a small number of modes efficient? This is the question. And then we found in like theorem 68 in this original Aronson and Arkhipov paper, we found the Gurwitz algorithm, which shows that actually finding these partial measurements for small number of modes is somehow difficult like that. So you can do it in this number of steps. So actually, it is not too difficult for just small k. In Gaussian boson sampling, we can observe that somehow if you evolve your Gaussian state till here, then if you ignore these modes, you just take the reduced density matrix, which is still Gaussian. And then if you have just a Gaussian state with just 2 modes, you can use this Lub-Hafnian's approach to find actually the distribution of photon numbers. So the conclusion is that finding the partial measurements or marginal distributions is classically efficient if we restrict ourselves to just maybe 2 or just small number of modes. Then the second part is maybe more difficult. We want to use compressive sensing algorithms to find the joint distribution based on these marginal distributions. And the question is it efficient? We would like to argue that it is. Okay, so now another digression about general concept of compressed sensing. So this is a thing that you have some results of some measurements. Let's say you measure some unknown signal, and you measure it using some, let's say, filters or patterns, which are now the rows of this matrix, this measurement matrix A. So measurement matrix A may be some like filters you apply to whatever you want to measure, and then after these filters you get some just number. So this is the measurement, the result of the measurement, and somehow this matrix A defines a set of measurements. And then it is that there is some signal you measure you want to find. Okay, so the problem is like that. Given results of measurements and a proper measurement matrix, you need to determine the measured sparse signal. So we assume that our signal we measure is sparse. So you need to distinguish it from all candidates that fit these results, because usually the problem for measurement matrices like this rectangular matrices, the Y is not unique. So maybe not like that. The results of the measurements don't uniquely determine the possible signal. But then if, okay. So for a given result of measurement and a given set of measurements, you probably have a lot of measurements, a lot of candidate solutions that fit. So you need to determine which is the real one from this set of all. And how we do that? We assume that we can order all these solutions according to their sparsity, or at least that we can find the most sparse among all these candidates. And then probably if the number of measurements is small, then the most sparse is not the real one. But if we add a few more measurements, you can eliminate a lot of these additional measurements give you more constraints, and somehow a lot of these old candidates which are not real will be removed. But you know for sure that the the real signal will be there forever for any number of measurements. So for some number of measurements, the most sparse solution is the real one. And then the question is how many measurements you need. And then people have different observations or theories, even strict mathematical theories that depend on the matrix A and actually and the way you determine the sparsity. They somehow allows you to find the number of measurements that is enough to determine the real signal which is measured, and the number of these measurements depends on the sparsity. So actually, for very sparse signals, so just a few non-zero entries, you may have just a few measurements. But for like less sparse or more dense matrix, you probably for less sparse signal you need much more measurements. Okay, so we'll continue adding measurement until the measured signal is the most sparse. So sometimes people estimate the number of measurements, and actually they observe that it scales linearly with the sparsity, while only logarithmically with the size of the vector. And then we need also some algorithm that determines the most sparse solution, the more sparse candidate solution. So people may use something like convex optimization, things like that, or some iterative algorithms. And I will focus on this iterative algorithm called matching pursuit. I will talk about this in a moment. Then there are many applications for this compressed sensing, so it is quite important thing. So what is matching pursuit? So here I repeat the scheme. Then matching pursuit is an iterative thing. You define something like the residue, which initially is your measurement matrix. Then initial solution is just 0. Then you have something like support detection. You need to determine which column of your measurement matrix is the closest to your residue. Because then if you find that this column, then it is probable that somehow there is a peak here at this position where the big column is. Then you need to update your residue, taking the difference between this old residue and the column you found. And you update your solution, adding just some value to in the position where you find this column the closest to the residue. And then you repeat everything. And we observe that in this iterative scheme, the most difficult part is this support detection, which is actually finding this column the most similar to the residue. And how we do that? We usually need to just multiply transposed measurement matrix by this. So because we are looking for the column which is the most similar to this, so we take the product of all columns and this. So this is the product of now rows, but there are columns of A times X. So we want to determine, we have just a long vector, and we just need to localize the maximum. So actually our complexity of the problem reduces to finding localizing the maximum of this very long vector. And so usually you can imagine that finding the maximum of a vector needs the number of steps, which is like the size of the vector. So if the vector is exponentially large, then also this is a difficult problem. But sometimes we can do it. So now I'm defining the so-called polynomial matching pursuit that I can apply to my boson sampling setup and somehow solve this crucial step, this support finding. So solve this step quickly. So here I write just all possible outputs from my boson sampling experiment. So I assume that in this case, from each mode, I can observe just 0, 1, or 2 photons. So I introduce some natural order in this set of all possible outputs. Then my real output is something like the distribution of some particular outputs. Okay, so now I see a lot of regularities in this set of all possible solutions, or all possible solutions. In particular, let me focus on this. Zeros in the fourth mode is like every third element is 0. So I can say that in mode 4, zeros are like tensor products of all ones with 3 long vector where you have in the first element 1. This vector has is non-zero in every third position. So you can observe that actually this pattern determines where are zeros in set of all possible solutions. And like very similar, you can discuss where are zeros in mode 1, which will be this pattern, where are ones in mode 1, which will be this pattern, and so on, so on, so on, so on. So like the structure of this set is very simple. Then you can do the same for like 0, 0 in mode 1, 2, or like 0, 0 in mode 3, 4. You observe that in mode 3, 4, 0, 0 repeats every 9th element, so it is like that. Okay, and then the probabilities of finding, let's say, 0 in the first mode is like a product of finding 0 in first mode of these patterns where are zeros in the first mode times your unknown vector x. So you have so now you can define your compressed sensing problem using this pattern as the measurement patterns. And so assume that I'm interested in this pairs of mode combinations of the outputs. So I compose my measurement matrix from these things. I can calculate the probabilities, which are products like that. I can calculate them from like known algorithms I mentioned before. And then we can observe that the crucial point in this matching pursuit was finding the maximum of this vector. But now if A has this particular structure, I notice that this is like finding the maximum of the sum of elements which are like that. But we can notice that this is nothing else than the Ising problem. So this is Ising problem for one-dimensional spin classical model, which is solvable in mn square steps. So in this way, we can say that if your measurements are like just marginal distributions for just two modes, then the problem of finding of like matching pursuit problem, complexity of this matching pursuit problem of finding the joint distribution from the marginal distribution is like the Ising problem, which is classically solvable, so we can do that. Okay, how it works in practice. So we take an initial state for our boson sampling as a vacuum state. So we do it in 0 Kelvin, in 0 temperature. So the initial state is just vacuum. Then we apply this Bogoliubov transformation people know. And then we measure just, let's say, nearest neighbors partial measurements. We calculate them from this loop Hafnian. And then we apply this polynomial-time matching pursuit. So how it works? For like formic acid, we consider a formic acid with just, let's say, 7 modes. We can calculate the spectra, the blue ones, exactly from the so-called Doktorov iterative method, which is for small molecules like that still efficient. So we can compare our result with this exact spectrum. And our result, this marginal distributions plus compressive sensing give you peaks like this orange. So we can localize the most significant peaks correctly, at least localize them, and then the intensities are also good. How it works for like larger molecules like thymine, we consider part of time a block of thymine with 26 modes, and then the size of the problem is now like maybe 2 or 3 to the power of 26. So we cannot deal with this Doktorov iterative method, at least using our like desktop computers. You can maybe do something with supercomputers. And then using our approach, measuring only marginal distributions, and then using this compressed sensing approach, we find these lines. And then we compare it with some other calculations of like precise calculations of this spectra, and we see that all these lines we recognize correctly. So this is recognized, then these 3, we have them, these 2, we have them exactly where they should be. So we found this thing for a molecule which is already non-trivial. Okay. Okay, so till now I talked about our results, and now I changed the topic and will speak about something like we just have an idea what to do next. So the question is, can quantum computing be helpful for compressive sensing? So we'll try to apply the same ideas we found to our previous problem. So I remind the scheme. I remind that for this crucial step of finding the joint distribution from marginal, we need to find the position of the maximum of a long vector. Yeah. So we can like if this vector is very sparse, so there are just a few, the just nearest neighbors measurements we discussed previously are enough to determine the joint distribution. But in general, if this the sparsity of the measured vector decreases, then we have just not enough data from just nearest neighbors measurements. So we need to add some data, like not necessarily nearest neighbors pairs, statistic of like photon numbers for not necessarily nearest neighbors. But then we cannot use our Ising approach because it was defined for like, it was effective for just nearest neighbors. Okay, so now forget about like Vibronic spectroscopy. Imagine that a long vector, the vector of size 2 to the power of n, and now imagine that somehow we just number all entries of this vector by using the binary representation of their position. So we have something like the scheme like that. So every element of this vector, so the position of every entry, is uniquely determined by a set of a few spins, like n spins. So you can see it like that. So then if you focus only on maybe 2 first spin and say that somehow we don't, or second and third, and we don't care about this and this, so this and this can be anything, just we fix these two, this down and this up. Then instead of just point, we have some pattern. Okay, then if we fix just these two, and we don't care about these two, we have another pattern, and then we can play this game with this, with like this spin fixed, and the rest is, let's say, whatever. Then we get another pattern. So we observe that configuration of all spins determines a point, and configuration of only chosen spins determine a binary pattern. And then assume that you can associate a number with each of these patterns. And this number can be, let's say, something maybe like the overlap with your original vector. Okay? So now assume that that these numbers are like overlaps with the original vector, and we know these patterns and these numbers, so we would like to apply the compressed sensing method using A composed of these patterns as a measurement matrix, and then these numbers will be the measurement vector. And we now observe that we can apply this matching pursuit algorithm and find that the maximum in the crucial step of the long vector is equivalent to the maximum over all paths of the, let's say, these numbers associated with each path, with each part of the path. Okay, and then if you look at it long enough, you can realize that this problem is nothing else than finding the configuration of spins with interactions given by these numbers. So this is interaction between first and second, interaction between second and third, and so on and so on. You also can consider something like the green. You fixed this and fixed this, and so you get some numbers which are something similar to interaction between the first and the third. And then this is not anymore the typical Ising problem, so you cannot solve it in polynomial time, but somehow it is a typical problem for a quantum annealer. So we think that quantum annealer actually under some conditions probably can help us to find this crucial step in our algorithm, and we can apply it to many problems related to compressed sensing. Okay, so that's actually all I wanted to say. I just wanted to show a few things about my institute, where I'm from. So it is NICT, National Institute of Information and Communication Technologies in Tokyo, and they work on like many different things related to information and communication technologies. Okay, sorry about this. This was again, so in particular, also they keep the standard of time and frequencies for Japan. And it's interesting, even sometimes you need to add an extra second to adjust your calendar year to the solar year. So then it's kind of event, we do it like publicly. So it's kind of adding the leap second to the year. Also, our institute has this quantum key distribution network for Tokyo. It's quite known of this, but we work on a huge range of problems. Okay, so the summary of my talk is like that. I work on boson sampling. I'm interested in when boson sampling can work as a simulator of vibrational spectroscopy. I observed that if the output of boson sampling is sparse enough, then the system can be simulable classically. For not sparse enough outputs, the method doesn't work, the classical thing. Then maybe we need something like more advanced things for solving the crucial steps, like quantum simulators like annealers. Okay, so this is all I wanted to say. I have some bibliography if anyone is interested. Thank you very much.
Thank you. Questions? Okay, so I can get started. So you had this kind of example where you have these molecules where you kind of estimate the spectra. Can we go back to the slide? So yes, so I think I see there are some small kind of deviations, even on the left-hand side and on the right-hand side. Do you have some explanation for that?
Between this and...
So on the left-hand side, the values are not always exactly where you want them to be. So I understand the blue values are the exact values, and the orange ones are kind of the compressed sensing values. And do you have some understanding why there is this deviation?
This in intensity. I think yes, because somehow you don't have enough data to determine this joint distribution accurately.
Okay.
So because we are restricted with just the data you can obtain from just nearest neighbors to apply this classical thing. And then sometimes for actually this with some much more small peaks, it is just not accurate. And so our method then can give you just like a first order approximation to the system.
So, and I think also on the right-hand side, I assume this kind of compares to some measurement data here?
Yes.
And some peaks are apparently missing, so if I don't know exactly how to, but I think it's, so I see some peaks in the measurement data which are not kind of, you cannot see in the compressed sensing, but probably the explanation is the same.
And the explanation is the same. It gives us just the first order method. Because also this matching pursuit is known to be quite efficient in terms of time, so it's very fast, but it is not very accurate. So people then develop much more maybe costly in time, but accurate method. And many of these methods are also have the same problem with finding like the support.
So would it be helpful to kind of add just a few higher order interactions to measure just a few of the higher order ones? Did you try something like that?
Actually, we think that so with just this method, it is not possible, but we think that somehow it will be for sure good to add more interactions, like not nearest neighbors, and somehow we can do it with this with this problem because it's small enough to simulate everything. So we can add whatever somehow marginal distribution we want, and we observe that actually yes, if you add just more data, you have better results.
Okay. Yes.
Thank you. Thank you for the talk. So my question is actually related to the previous question. So I was wondering, in a realistic scenario, your harmonic oscillator is slightly anharmonic. But here, I assume you cannot model that because you assume that you have a perfect harmonic.
We assumed like bosonic thing, and yeah.
So could it be that the deviation, to a large extent, is coming from this anharmonicity?
Maybe we can. Maybe we can do something, but now I don't know.
Okay. Thank
maybe
you.
Yes, maybe yes.